Today, we're going to dive into a concept from physics that's pretty much hiding in plain sight. It's everywhere, from your sunglasses to the most advanced lasers. We're talking about a single word that, believe it or not, has two totally different meanings that are also deeply connected. That word is polarization. So let's unravel how it all works.
You've probably heard the term a million times. Maybe you even own a pair of sunglasses that claim to cut glare like magic. But have you ever stopped to think about how they really do it? What's the invisible process happening inside those lenses? Well, the answer is genuinely fascinating, and that's exactly where we're going to start.
And here's the twist. To really get what's going on with those sunglasses, you first have to understand that in the world of physics, polarization means two very distinct things. One describes what happens inside a material, and the other describes a property of light itself. Getting these two straight is the key to unlocking the whole thing.
So let's meet these two faces of polarization. We're going to break them down one by one, and then we'll see how they come together to create some truly amazing technology.
Okay, so on one hand, we have the polarization of materials. This is all about what's happening at the atomic level, when you hit a substance with an electric field. Then on the other hand, you have the polarization of light, which is all about the direction that a light wave kind of wiggles as it flies through space. See? Two very different ideas, but they share the exact same name.
All right, first up, let's zoom way in, right into the microscopic world of materials. We're going to talk about how things like glass or plastic respond when an electric field shows up.
Now, the key thing to get here is that in materials like glass or plastic, what we call insulators, the electric charges can't just roam around freely like they do in a metal wire. Nope, they're bound to their atoms. But an external electric field can still give them a little nudge, forcing the positive and negative charges to shift just a tiny bit apart. And that tiny forced separation, that is material polarization.
In this image shows it perfectly. Look at the top. With no electric field, the molecules in both the solid and the gas are all just pointing in random directions. But now, look what happens on the bottom when we apply that field. Boom! The positive ends of the molecules get pulled one way, and the negative ends get pulled the other. They all line up, and just like that, the entire material becomes polarized.
At its core, this whole relationship can be boiled down to a pretty simple equation. Now, don't worry about the symbols. All this is really saying is that the polarization of the material, which we call P, is directly tied to the strength of the electric field we apply, E. Or, to put it even simpler, a stronger field forces a stronger alignment of those charges. It's a really direct and, honestly, beautiful connection.
All right, let's completely shift gears. We're leaving the world of materials for a minute and moving on to the second meaning of our favorite word today, the polarization of light itself. So light travels as an electromagnetic wave. And the crucial part is that it's a transverse wave. That just means it oscillates, or wiggles, perpendicular to the direction it's traveling. Think about shaking a rope up and down. The wave moves forward, but the rope itself is just wiggling vertically. Well, the polarization of light is simply the specific direction of that wiggle. And that wiggle can actually take a few different forms. The three main types you'll hear about are linear, circular, and elliptical. Each one is just determined by how the different components of the light wave are interacting with each other as they fly along. Let's break them down.
Linear polarization is the simplest one to picture. Let's go back to our rope analogy. If you only shake that rope straight up and down, that's it. That's linear. For light, this happens when all the components of the wave are oscillating perfectly in sync. They hit their peaks and their valleys at the exact same time. We say they're perfectly in phase.
Now, for circular polarization, things get a little more interesting. The electric field doesn't just wiggle back and forth, it actually rotates in a perfect circle as the wave moves forward. This is a special case, though. It only happens when two specific conditions are met. The wave components have to have the exact same strength, and they have to be exactly 90 degrees out of sync, or out of phase with each other. So what happens if the components are out of phase but they don't have the same strength? Well, that's when you get elliptical polarization. The electric field still rotates, but it traces out an ellipse instead of a perfect circle. This is actually the most common or general form of polarized light that you'll find out in the wild. Okay, so we've met our two different types of polarization: the shifting of charges inside materials and the orientation of the wiggles in light waves. Now for the most exciting part. How on earth do they connect?
And this, right here, is where our two worlds collide. It turns out we can actually engineer materials with very specific internal structures, that's our first type of polarization, to interact with and control the wiggle of light passing through them, our second type of polarization. This is the fundamental secret behind how we filter, change, and manipulate light.
Let's look at a real-world example of this. This is a Glan-Thompson polarizer. On the left, you have unpolarized light coming in. It's got wiggles in every direction. It enters this specially cut crystal. Now watch what the crystal does. It actually splits the light into two different polarization states. Notice how one state is allowed to pass straight through, but the other one gets reflected away at that internal air gap. It's a physical filter for light waves, literally sorting them by their wiggle. And it's not just about filtering either. We have a whole toolkit of optical components for this. Polarizers, like the one we just saw, act like gates. Then you have things called half-wave plates that can actually rotate the angle of linearly polarized light. And quarter-wave plates are even cooler. They can change linear polarization into circular and then change it right back again.
So, we've covered a lot of ground here. We've looked at two distinct definitions of polarization and, most importantly, how they link together. But why does any of this really matter? What's the big deal?
Well, understanding this interaction is absolutely fundamental to so much of our modern technology. It's essential for designing stable lasers. We use it to kill unwanted reflections and glare using techniques like Brewster's angle. It's the basis for scientific instruments like spectrometers and for building ultra-fast optical switches. And yeah, it brings us right back to where we started, making polarized sunglasses.
When you really think about it, polarization is like a hidden language that allows materials and light to communicate with each other. By learning to understand it, we've built the entire modern world of optics. And it really makes you wonder, as we get even better at speaking this language, what new technologies are just waiting around the corner to be invented.